Okay, good morning, students. So another video of counters we will see now. Okay, so this let me start sharing my screen. Hope you're all able to see my screen. Okay, so now we know the introduction about sequential circuits. Um, it works with a memory with its feedback loop, and the output depends on both the input and the past output. Okay, in certain cases, certain circuits, you need to remember the past output. Only then, you'll be able to continue the series, a sequence kind of. So those kinds of applications definitely require a sequential circuits. So for example, imagine that you have a counter applications, you wanted to count a certain number. Only if you know where you have stopped, you'll be able to proceed with the simple adder application circuits. So now today, what are we going to see is a counter circuit. Okay. So these counters, there are so many different kinds of counters, like how we have seen the categories in sequential circuits. Counter comes under a sequential circuits, and here mainly these circuits are used for counting purposes. Okay. So when you're doing these counting operations, you can think about very wide applications that fall here in the counter. Counter is the widest application of flip-flops. Okay, you take any flip-flop, the predominantly used applications could be these counters. Okay, so generally these are a group of flip-flops. How do you decide the group size? Based on the counting number. Okay, and these flip-flops will have a clock signal either applied to all the flip-flops or to the first flip-flop. Therein, it is given in the sequence. So depending upon this, they are categorized into two types: synchronous counter and asynchronous counter. Asynchronous counter has got another name called as a ripple counter. So now our concentration for this particular video will be on ripple counters, or in other words, asynchronous. From the word you must have guessed right now, all the flip-flops are not going to be connected to the same external clock signal. So only the first flip-flop, okay, in the series of the counter is a series of group of flip-flops, right? So only the first flip-flop will be connected directly to the external clock signal in the case of asynchronous. Whereas in the case of synchronous, all the flip-flops will be given the same clock signal connected directly as the input. Okay. So now let's go ahead. So as we discussed till now, this is a very simple digital electronic circuits used for counting purpose. So that counting purpose, the series in which you need to do the counting decides the type of the counter. So right now we are seeing the up counter as an example. So if you want to count a number from zero, say for example 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, then it's called as an up counter. Similarly, when you wanted to count downwards from 10 to 0, 10, 9, 8, 7, 6 goes on, then it is called as a down counter. So depending upon the application, you can configure the circuit design. So let's go and do one counter right now. uh, yeah, these are all the terms and key parameters you need to remember before going to any kind of a counter design. The first one is a clock input. We all know that sequential circuit has a memory unit, and here in these circuits you will have a clock input. The clock input is the one which triggers the data that is present inside these memory units or the flip flops. Okay. So in the case of the asynchronous counter or the ripple counters, only the very first flip flop will receive the external clock. The other flip flops will be connected in series. So the output of one flip flop will act as the clock for the next flip flop. It goes on. Whereas in the case of synchronous circuit, all flip-flops will receive the same clock. The second condition is how do they operate? What is the condition of the operation? Flip-flop will toggle one after another, causing a ripple effect in the case of asynchronous counter. Okay. Whereas in the case of synchronous counter, all flip-flops toggle together. What do you mean by this word toggle? Whenever there is a shift in the data that is present inside the flip-flop, So when you're experiencing a flip, when a zero inside the flip flop is able to undergo a one, a change in the data. Similarly, a one is undergoing a zero. In those conditions, you will have a toggling effect. Similarly, the speed slower you make the propagation delay. Okay, the ripple effect, the propagation delay will vary. Okay, so all the flip flops will not change at the same time. So so when you're going to compare synchronous and asynchronous counter, synchronous counter is very very fast, because you need not wait for the previous flip flop to give the output of the output, and that output will act like a trigger to the next flip flops, right? So it has to wait for a certain amount of time in the case of asynchronous, whereas in synchronous, every flip flop is getting the input at the same time, so it is very very faster. Okay, so you may now realize that the propagation delay is very heavy in the asynchronous counter, whereas it is almost the same that is set for in the case of the synchronous counter. Circuit complexity. When you think about the complexity, the ripple counter is one of the simplest one, which we are going to see now in the next few slides. Whereas synchronous counter are complex because they need additional circuits to maintain the a specific propagation delay and the speed and the design. But then your asynchronous counter are very less accurate. They are prone to delays. Sometimes you may land up in a wrong number when it is doing the counting. So it is not so much accurate. You can experience a issue when there is a propagation delay that is happening at a larger scale. But then synchronous counter are very accurate. You can rely on the data that it is being released. Next, the direction of the counting. Usually, the up counter, as we saw just now, does the counting through an ascending order, and the down counter does the counting in the descending order. So the up counters will initially start only from zero state. Okay, whereas the down counters, initially you have to set the flip flop. Once you set the flip flop, it will go to the maximum value of what you have designed the flip flop. Okay, suppose imagine that you're trying to develop a 3-bit flip flop. Okay, then it will start from 000 in the case of an up counter. Similarly, the down counters will all be set and tuned to 111. Okay, from the maximum point it will start. And the triggering, this is the very important point you need to remember when you're designing the circuit. You need to remember when a trigger is applied, when the clock is going to be triggered. So the triggering point will determine when the data changes. Okay, whenever a trigger happens, only then there will be a shift in the output of the flip flop. Okay, you know the different types of clock triggering: level triggering, edge triggering, and in the level triggering itself, positive level triggering, negative level triggering. So all these decides the flip flop triggers. And then let's go to the design part. Okay, we have got two things to remember here. We are going to see the design of an up counter and a down counter, and we will take an example of 2-bit ripple counter. So it's just going to count only 0 1 2. Okay, 1 2 3. So in a 2-bit triple counter, you will be able to get four straights. Okay, 0 1 2 3. Okay, so now we are trying to design this using a toggle flip flop. Why toggle flip flop? From the word toggle, we know that the flip flop changes only when there is a toggle. So toggle flip flop really achieves it. The design is very simple. Also, we can design the same flip flop using a JK flip flop, because JK flip flop, when you both are connected to logic one, how does the truth table works in a JK? You get a toggling effect, right? So you can also design it using a JK flip flop, connecting both J and K to a permanent logic one. And then let's see this design now. Okay, so there are two T flip flops, okay, connected in series, and you have one input T, and this is the first flip flop, flip FFA. Flip flop A is the first flip flop, and next one is second flip flop FFB. Okay, how many inputs you have? You've got two inputs. One is the flip-flop input T, and another one is the clock signal. You sometimes you will also have a clear signal which clears all the previously stored data. So in this example, we are seeing only two inputs. P is in one input, another one is the clock signal input. And you could see a bubble here that says that the clock signal is given at the negative end. So in other words, it is negative triggered. Okay. When does a negative trigger happen? Whenever you have a shift that is happening from 0 to 1. Okay, that is negative trigger. When does the clock signal, whenever the clock drops from logic 0, I'm sorry, logic 1 to logic 0 downwards. Okay, so that is how trigger happens. Okay, so when the case of positive trigger, how does a positive trigger work? Whenever the clock signal moves from logic 0 to logic 1 up direction, so that is what is your um, positive triggering. So now let's go ahead. Before going, you must have noticed the output of the first flip-flop is given as the input to the second clock signal. Okay, so this particular flip-flop will undergo a toggling effect only when there is a data change in this particular first flip-flop output. Okay, but you could see that both the flip-flops are connected to logic 1, so both gets the input, but then when does the this particular flip-flop will be triggered? Only when there is a toggling effect, when there is a shift in the data here in this particular first flip-flop. So now let's see the example. Okay, uh, so in the first case, we are initially setting, it's an up counter. It has to start counting from 0, 0, right? So we are initializing all the flip-flop outputs to 0. Okay. And you need to remember where the clock is applied, that is your LSB bit. Okay. Where which flip-flop the clock is applied, that is the LSB bit. And the other end is your MSB bit. So this is your MSB bit. So now we are starting from 0. Okay. So now here, whenever a toggle, already you have a 0. So what will be the next output here for this particular flip-flop? From 0, it will change to 1 when the next clock pulse is given. So now a next negative trigger clock pulse is given, and you're getting an output like 1 here. So now here that it undergoes a shift, but how is that shift happening? It's coming from 0 to 1. So now, is it a negative or a positive trigger? The data here is shifted from 0 to 1. Okay. So now we are undergoing a what kind of a shift? Are you all able to realize? 0 to 1. So it is undergoing a positive trigger. It is the clock pulse is moving from logic 0 to logic 1 high. So it is a positive trigger. But here you have connected it to a clock signal is connected to a negative, so that it will not undergo any triggering effect. This clock pulse will not be triggered at all. So there will be no change in the output of this particular flip-flop. So you will receive the same output. Is it all fine? So now the next clock pulse is applied. When the next clock pulse is applied here, the output will be toggled in this, because it's a toggle flip-flop. The output will be toggled. So from 1, you will get a 0. So now we have got a 0. So now what has happened? This particular output has come from 1 to 0. So that is given to the clock, right? Negative clock. So now you should think from the clock pulse is now acting like it has undergo a shift from logic 1 to logic 0. Okay. So it is negatively triggered now. So when it is negatively triggered, the data what is present in this flip-flop will be toggled. So already what is the data that is present inside this flip-flop? A 0 is present. So now it will become 1. Okay. Now apply the next clock pulse. When the next clock pulse is applied here, this flip-flop will give you an output. The output will be shifted from 0 to 1. Okay. So now what has happened? this output is changed from toggle from 0 to 1. So from logic 0 to 1, it is in the positive direction. So this particular clock will not be triggered because you are giving it to a bubble. Bubble means a negative trigger only will be activated. So from 0 to 1, it will not activate. So whatever data was already previously present, the same data will remain. So already what did you have? 1 was stored, the same 1 will be stored. Okay. Now again you're applying the clock pulse. When the clock pulse is applied from this output, earlier this flip-flop had 1, so from 1 it will undergo a change to 0, the first flip-flop. Now what has happened, the first flip-flop has changed from logic 1 to logic 0. So you are undergoing a negative trigger. The negative trigger is applied to the second flip-flop. So the data that is present in the second flip-flop now will be toggled, and you will get from logic 1, it will toggle to logic 0. So the same step continues. We have already started with 0 0, right? Now we are ending here with 0 0. What will happen? The same sequence will go on. Okay. Like I said, wherever the data that is connected, that is the LSB bit. Okay. So this is your LSB bit, and the rear end is your MSB bit. So now let's see what's the data that we have got. 0. So LSB, we have to start from 0, this particular point, right? Yeah, 0 0 0 1 1 0 1 1. Again, the counter is again getting back to 0 0. So now we have achieved the counting effect. It is able to count all the 4 states of the 2-bit triple counter. Suppose you wanted to count all the, imagine you wanted to develop a counter to count all the 8 states, then what do you have to do? You need to add another one flip flop, third flip flop. So you'll be able to get all the 8 states, 0 0 0 0 0 1, things like that. Okay, you'll be able to do. So if it is going to be 16 states you wanted to count, then you connect it to 4 flip flops. Okay, same operation we have seen it for 2 flip flop. Now let's go for the so if the same thing whatever we saw now, it's given directly here in this particular table. This will be easy for you. What did we do? First we initialized all the flip flops outputs to 0 0. Then only when there is a negative clock, there will be a shift in the toggling effect will be happening in the second flip flop. So we are seeing what happens in the first clock pulse, second clock pulse, third clock pulse, fourth. How are we getting the data? Whatever we saw just now is explained here. Next, we are going to see the same ripple up counter using a JK flip flop. So instead of T flip flop, if you wanted to design it using a JK flip flop, then JK, when does it undergo a toggling effect? When both J and K are connected to logic high, 1 and 1, the truth table works like a toggle, right? You get a toggle. So instead of using a T flip flop, the same effect can be achieved when both J and K flip flops are connected to logic high. So here also you could see, just remember there is one bubble that is missing here. Both the clock has to be given to a negative edge only. So you need to include one clock. Before that clock, there should be a bubble in both these flip flops, okay? Included, and the output of one flip flop is given as the input to the second flip flop. It goes on. Okay, so now let's do the same operation. When you're going to start with the first flip flop, what will you do? You will initialize it to 0 0. Okay, and next we are going to again apply the clock signal. When a clock signal is applied and the inputs are already 1 and 1, what happens? This output will toggle. This particular flip flop, the first flip flop will toggle. So already what is the data that is present? 0 is present. Okay. Now that 0 will become 1. Okay. And in this case, what are we having? You are, this is given to the negative edge triggered. So from 0 to 1, it is positive, right? You're moving from logic 0 to up direction, so it is not a positive trigger, so it is not going to affect the second flip flop. So whatever data was already present, the same data will continue. Okay, 0 was already present, so it is not going to toggle because the trigger is not applied. So we'll go to the third clock pulse. When you're applying the third clock pulse, this particular uh, you're giving a negative clock pulse, right? Directly. So what happens? This particular JK flip flop will undergo a toggle. So from 1, it shifts to 0. Now what happens? This particular output, first flip flop output, is undergoing a toggle from 1 to 0. So negative edge is activated. Okay, so in this negative edge, when it is activated, this particular flip flop will be toggled. So from 0, it will shift to 1. Okay, similarly, you're applying the fourth clock pulse, and the fourth clock pulse is applied, the data here will be shifted. So from 0 to 1, you get. Okay, so now 0 to 1, it is in the rising direction. So pause, it will not trigger the second flip flop. So the same data will be repeated. Okay, now let's go and see we will apply clock once again here. So the output will change from 1 to 0. Now what happens? This will be activated, a trigger will happen because the output is toggled from 1 to 0, a falling edge. From 1, it is fallen to 0. So the clock will be triggered at this point. Okay, the clock signal. So you will be able to have a shift in the data that is already present. Already you have got 1. Now this will become 0. Is it all fine? So we have achieved the same thing. We have started with 0 0. Next straight is 0 1 1 0 1 1. Again, it is going back. The counter is going back to 0 0. It will start counting. Okay. So you're able to get this decimal counter 0 1 2 3 again 0. We are able to achieve this. Now let's see a down counter. Down counter is just the reverse operation. Only thing you need to remember is here you will initialize the outputs of all the flip flops to logic 1 instead of logic 0. We will start from the maximum point. Okay. So it's a 2-bit triple counter. So what's the maximum state that is possible here in a 2-bit? 1 1. So we will initialize both the flip flops to 1 1. And the same operation what we saw, and you will get the output as 1110. I'm sorry, 1110. This is something wrong. This should be 0 1, and then the last one is 0 0. Okay, again it will go from 1 1 onwards. With this I stop.